You are listening to Distributed by Design, Apache Cassandra for the modern developer. Like and subscribe to keep up to date on our latest audiobooks. Distributed by Design, Apache Cassandra for the modern developer. Chapter 1, The Call to Scale, Why Modern Developers Choose Cassandra. 1.1, The Data Tsunami, Challenges of Modern Applications. In today's digital landscape, we live in a world awash with data. Every click, every swipe, every sensor reading contributes to an ever-growing deluge. Modern applications are expected to perform flawlessly under immense pressure, handling unprecedented volumes of information, delivering real-time responses, and maintaining availability around the clock, across the globe. From social media feeds updating in milliseconds to critical financial transactions processed in an instant, user expectations are higher than ever. Consider an online retailer. They need to manage millions of product listings, process thousands of orders per minute, track inventory across multiple warehouses, and personalize recommendations for each customer based on their browsing history. All of this must happen seamlessly, constantly, and without interruption. This is the data tsunami, encompassing not just the sheer volume of data, but also its velocity, the speed at which it's generated and processed, and its variety, the diverse formats and sources. Traditional approaches to data management, while foundational to computing, often struggle to meet these extreme demands. 1.2 Relational databases, the pillars and their limits. For decades, relational databases, powered by the structured query language or SQL, have been the backbone of nearly all serious applications. They are designed for strong consistency, ensuring that every piece of data adheres to predefined rules and relationships. Their ACID properties, atomicity, consistency, isolation, and durability guarantee reliable transaction processing, making them ideal for mission-critical systems like banking applications where data integrity is paramount. Relational databases shine when dealing with structured data where relationships between different entities are crucial and complex queries involving multiple tables, known as joins, are frequent. They enforce strict schemas, ensuring that data fits a predefined mold. However, as data volumes exploded and global, always-on applications became the norm, the limitations of this paradigm began to emerge, primarily in terms of scalability and availability. Scaling a relational database horizontally, meaning adding more machines to share the load, is notoriously challenging. This often involves complex sharding techniques where data is manually split and distributed across multiple database instances. This adds significant architectural complexity, administration overhead, and can still create bottlenecks. The alternative, vertical scaling, simply buying a bigger, more powerful server, eventually hits physical and economic limits. Furthermore, traditional relational databases often have a single point of failure. If the primary database server goes down, the entire application can cease to function, impacting availability. While replication mechanisms exist to provide failover, they can add complexity and often involve trade-offs in performance or consistency during switchovers. The always-on global expectation demands a different architectural approach. 1.3 Enter NoSQL, a new paradigm, to address the shortcomings of relational databases in handling massive, highly available, and diverse datasets. A new category of database emerged in the early 21st century, NoSQL. The term NoSQL stands not for NoSQL, as some might assume, but rather not only SQL, signifying that while SQL databases still have their place, they are no longer the sole solution. NoSQL databases represent a paradigm shift. They typically relax some of the strict consistency guarantees of relational databases in exchange for massive scalability, high availability, and the ability to handle unstructured or semi-structured data more flexibly. This trade-off is often summarized by the CAP theorem, a fundamental principle in distributed computing. The CAP theorem states that a distributed data store can only simultaneously satisfy 2 out of 3 guarantees: consistency, availability, and partition tolerance. Consistency: every read receives the most recent write or an error. Availability: every request receives a response without guarantee that it contains the most recent write. Partition tolerance. The system continues to operate despite arbitrary numbers of messages being dropped or delayed by the network between nodes. In the real world, network partitions are inevitable. Servers go down, network cables get cut, and internet connections fail. Therefore, any distributed system must be partition tolerant. This leaves a choice between consistency and availability. Relational databases typically prioritize consistency over availability in the face of a partition. Many NoSQL databases, including Cassandra, lean towards availability over strict consistency, opting for what is known as eventual consistency. This means that while data may not be immediately identical across all replicas after a write, it will eventually converge to a consistent state. NoSQL databases are organized into different categories, each optimized for specific data types and access patterns. Key value stores. Simple data storage where each item is stored with a unique key, like a dictionary, e.g., RIDIs. Document databases. Store data in flexible, semi-structured documents, e.g., JSON, ideal for content management or catalogs, e.g., MongoDB. Graph databases. Optimized for storing and traversing relationships between entities, e.g., Neo4j. Column family stores store data in rows, but columns are grouped into column families. This is where Apache Cassandra fits. 1.4 Introducing Apache Cassandra, distributed by design. Apache Cassandra is an open-source, distributed, wide-column store NoSQL database management system designed to handle large amounts of data across many commodity servers, providing high availability with no single point of failure. It offers robust support for clusters spanning multiple data centers, making it a powerful choice for applications requiring global reach and continuous uptime. Cassandra's core strengths lie in its architectural choices. Decentralization. Every node in a Cassandra cluster is identical. There's no single master node. This peer-to-peer architecture eliminates single points of failure. High availability. Due to its decentralized nature and robust replication, Cassandra can sustain failure of individual nodes or even entire data centers without interrupting service. Data is always accessible. Massive scalability. Cassandra is designed for linear scalability. This means you can increase your capacity, both storage and throughput for reads and writes, simply by adding more commodity servers. There's no theoretical limit to how large a Cassandra cluster can grow. Fault tolerance. If a node goes down, Cassandra can automatically route requests to available replicas, and when the down node recovers, it will automatically resynchronize with the rest of the cluster. Eventual consistency. Cassandra is built for highly concurrent writes across multiple nodes. It achieves consistency through reconciliation, ensuring that all replicas eventually converge to the same state. This trade-off enables exceptional write throughput and availability. Cassandra differs fundamentally from a relational database. There are no joins, no foreign keys, and generally, no complex transactions spanning multiple data entries. Instead, it prioritizes fast, direct access to data based on its primary key and efficient distribution of data across a vast network of machines. 1.5 Where Cassandra shines. Key use cases. Cassandra is particularly well suited for applications that demand high write throughput. It can ingest data at extremely high rates, making it ideal for Internet of Things, IoT, sensor data, real-time analytics, and logging systems. Always-on availability. Companies that cannot tolerate downtime, such as global streaming services or critical financial systems, leverage Cassandra's inherent resilience. Massive scale. Applications storing petabytes of user data, activity feeds, or historical records find Cassandra perfect for growing without limits. Time series data. Its efficient handling of data ordered by time makes it excellent for storing metrics, events, and historical trends. User profiles and personalization. Storing and quickly retrieving user-specific data, preference settings, and personalized recommendations. It's not a silver bullet, however. If your application relies heavily on complex multi-table joins, ad hoc analytical queries across your entire dataset, or requires strict ACID transactions across multiple records. A relational database or a specialized analytical database might be a better fit. 1.6 A brief history. From Facebook to open source. Apache Cassandra began its journey at Facebook in 2008, designed to power the social media giant's inbox search feature. Faced with the challenge of building a highly available and scalable search index that could handle enormous write volumes for millions of users, Facebook engineers developed Cassandra, drawing inspiration from Google's Bigtable and Amazon's Dynamo distributed storage systems. In 2009, Facebook open-sourced Cassandra, donating it to the Apache Software Foundation. It quickly gained traction within the open-source community and has since evolved into a robust, widely adopted database. Its decentralized architecture and impressive scalability have made it a cornerstone for companies dealing with unprecedented data volumes and high availability requirements. 1.7 Case Study Spotlight. Netflix's story of availability. Perhaps one of the most compelling real-world examples of Cassandra's power comes from a company that has fundamentally changed how we consume entertainment. Netflix. In the early 2010s, Netflix, like many rapidly growing tech companies, faced a severe challenge with its monolithic relational database infrastructure. As their subscriber base exploded and streaming became their primary business, a single relational database instance could no longer handle the immense load and provide the necessary resilience. Downtime, even for a few minutes, meant millions of frustrated users and significant financial losses. Netflix's solution was a bold leap into distributed systems, and Apache Cassandra became a crucial component of this transformation. They adopted Cassandra specifically for its promise of extreme availability and horizontal scalability. They realized that for many of their critical services, such as user profiles, viewing history, and stream state management, the ability to always serve a request, even if it meant tolerating brief eventual consistency, was far more valuable than strict, immediate data consistency that could come at the cost of downtime. By migrating vital services to Cassandra, Netflix built an architecture that could withstand failures of individual servers, racks, or even entire data centers, without interrupting the user experience. Imagine a scenario where an electrical grid failure knocks out an entire region. Because Netflix's data is replicated across different geographic data centers using Cassandra's robust capabilities, users elsewhere can continue streaming without interruption. This focus on always-on availability, enabled by Cassandra's distributed design, became a cornerstone of Netflix's unmatched reliability in the streaming world. Their story highlights Cassandra's real-world impact in delivering seamless service at massive scale. 1.8 Looking ahead, what this book will cover. This chapter has provided a high-level overview of why Apache Cassandra emerged and its fundamental strengths. As a developer, your journey with Cassandra will involve much more than just understanding its architecture. It will demand a shift in how you think about designing and interacting with your data. In the chapters that follow, we will guide you through the practical aspects of building applications with Cassandra. We'll delve into understanding Cassandra's architecture in more detail, how it distributes data, replicates it, and maintains its always-on nature. The crucial art of data modeling, learning to design your tables not around relational principles, but around the queries your application needs to perform, which is the key to Cassandra performance. Mastering SQL, the language you'll use to interact with Cassandra and how it differs from traditional SQL. Connecting your applications, how to use client drivers in popular programming languages to efficiently send and receive data from Cassandra. Common patterns and operations, practical examples of creating, reading, updating, and deleting data, and how to handle special cases like counters and lightweight transactions. Optimizing for performance, strategies for ensuring your Cassandra applications scale efficiently and perform under load. Avoiding common pitfalls, understanding anti-patterns that can lead to performance issues and how to design robust solutions. Monitoring and troubleshooting, essential tips for keeping your Cassandra applications healthy and debugging issues. Real-world case studies, deeper dives into how Cassandra is used by leading companies to solve complex problems. By the end of this book, you will have a comprehensive understanding of Apache Cassandra from a developer's perspective, equipped to design, build, and optimize highly scalable and available applications. Let's begin. Suggested further reading. The original Apache Cassandra website. Explore the official project documentation for the most up-to-date and authoritative information on Cassandra's features and architecture. DataStax Academy. DataStax, a company built around Cassandra, offers numerous free online courses and comprehensive documentation that delves deeper into many of the concepts introduced here, with a strong focus on practical application. Dynamo, Amazon's highly available key-value store by Giuseppe Candia et al. This seminal paper describes Amazon's internal distributed key-value store, Dynamo, which heavily influenced Cassandra's design. Understanding Dynamo provides a deeper conceptual foundation for Cassandra's distributed nature. Netflix Tech Blog. Search for articles specifically related to Cassandra on the Netflix Technology blog. These often provide invaluable insights into real-world scaling challenges and solutions. Chapter 2. Inside the Ring. Understanding Cassandra's distributed architecture. Apache Cassandra's power lies in its unique architecture, a distributed system designed from the ground up for high availability and linear scalability. To truly build effective applications with Cassandra, you first need to understand how it organizes and manages data across a network of machines. Let's peel back the layers and look inside the Cassandra ring. 2.1 The building blocks. Nodes, clusters, and keyspaces. Imagine a Cassandra deployment not as a single, hulking database server, but as a collective of independent yet collaborative units. These units are its fundamental building blocks. Node. At its simplest, a node is a single instance of the Cassandra database running on a physical or virtual machine. Each node holds a portion of the cluster's data and participates in all operations. Cluster. A cluster is a group of interconnected Cassandra nodes working together as a single, logical database system. When your application connects to Cassandra, it connects to the cluster as a whole, not just an individual node. Keyspace. This is your logical container for data within a Cassandra cluster, similar to how a database or schema might function in a relational system. A keyspace defines the replication strategy, how many copies of your data are kept, and the replication factor, how many copies for all the tables within it. You might have separate keyspaces for different applications or different parts of a large application, each with its own data replication rules. Data center rack. In larger, production deployments, clusters often span multiple physical locations, data centers, or logical failure domains within a location, racks. Cassandra is aware of these topologies. This awareness allows it to intelligently place copies of your data, replicas, in different racks or data centers, ensuring that a power outage in one rack or a natural disaster in one data center doesn't lead to data loss or service disruption. 2.2 The Cassandra Ring. Consistent hashing and data distribution. At the heart of Cassandra's data distribution is the concept of the ring. Imagine all the nodes in your cluster arranged in a circular fashion. Each node is assigned one or more tokens, which represent a specific range of data on this conceptual ring. When your application writes data to Cassandra, the database performs a hash calculation on your data's partition key, which we'll discuss in detail in the next chapter. This hash result determines which token range the data falls into, and thus, which node is primarily responsible for that piece of data. This mechanism is called consistent hashing. For instance, if you have a table storing user profiles, and the user's ID is the partition key, Cassandra will hash each user ID. A user whose ID hashes to a value between, say, 100 and 200 will be assigned to a node responsible for that token range. The beauty of this ring architecture is its elasticity. When you add a new node to the cluster, it claims a section of the token range, and data is automatically rebalanced from its neighbors to the new node. Conversely, if a node is removed, its token range is absorbed by its neighbors. This automatic data rebalancing is one of the key reasons Cassandra can scale horizontally with minimal operational overhead. There is no central orchestrator that needs to be manually reconfigured. The nodes figure it out among themselves. 2.3 Replication, ensuring data availability and durability. While consistent hashing determines which node owns a piece of data, replication ensures that there are multiple copies of that data distributed across the cluster. This is fundamental to Cassandra's high availability and fault tolerance. Replication factor, RF. This defines how many copies of each row of data Cassandra will maintain in your cluster. If your keyspace is configured with a replication factor of 3, every row you write will have 3 identical copies stored on 3 different nodes. If one node becomes unavailable, the other 2 copies are still there to serve requests. Replication strategy. The way these data copies are placed is governed by the replication strategy defined for your keyspace. Simple strategy. This is used for single data center deployments. It simply places replicas on consecutive nodes in the ring. Network topology strategy. This is the recommended strategy for production environments, especially those spanning multiple data centers. It allows you to specify the replication factor for each data center independently. For example, you might tell Cassandra to keep 3 copies in your US/East data center and 2 copies in your Europe data center. Cassandra then intelligently places replicas so that they reside on different racks and data centers, maximizing resilience. If an entire data center goes offline, your data remains safe and available in other data centers. 2.4 Consistency levels, the read-write dance. Even with multiple copies of data, a critical question remains. When you write data, how many copies need to acknowledge the write for it to be considered successful? And when you read data, how many copies do you need to consult to ensure you're getting the most up-to-date information? This is governed by consistency levels, CLS. Consistency levels are configurable per query by your application. This allows you to choose the right balance between consistency, availability, and latency for each operation. 1. For writes, only one replica needs to acknowledge the write. For reads, data is returned from the fastest responding replica. This offers the best performance and highest availability, but the weakest consistency. Useful for fire and forget data like activity logs or non-critical sensor readings, where some eventual inconsistencies are acceptable. Quorum, this is a commonly used consistency level. For writes, a majority of replicas, more than half of the replication factor, must acknowledge the write. For reads, the coordinator node requests data from a majority of replicas and returns the most recent version. With a replication factor of 3, Quorum requires 2 acknowledgements. It offers a good balance between consistency and performance for many applications. All replicas must acknowledge a write. For reads, data is returned only when all replicas respond. This provides the highest consistency, strong consistency, guaranteeing that you'll always read the latest data. However, it comes with the highest latency and lowest availability, as the failure of even one replica will cause the operation to fail. This is rarely used in production for typical application interactions. LOCALQRUM, used for multi-data center deployments. It's similar to Quorum, but only applies to replicas within the local data center. This is highly beneficial for global applications, allowing you to get a consistent read or write experience in your local data center without incurring the latency of waiting for remote data centers to respond. Each quorum, another multi-data center option, requiring a quorum acknowledgement from each data center. This offers very strong consistency globally, but at a higher latency cost. Cassandra also has a self-healing mechanism called read repair. If your application requests data with a certain consistency level, and Cassandra observes that some replicas return an older version of the data, it will return the most recent version to your application while asynchronously updating the out-of-date replicas in the background. This helps maintain eventual consistency across the cluster. 2.5 The peer-to-peer model, gossip and decentralization. One of Cassandra's defining characteristics is its peer-to-peer nature. There's no single master, leader, or name node. Every node in the cluster is functionally identical and can handle any client request for data. This decentralization is made possible by the gossip protocol. This is a communication mechanism where nodes periodically exchange information about their own state and the state of other nodes they know about. This gossiping behavior ensures that every node eventually learns about the health, location, and status of every other node in the cluster. If a node goes down, the other nodes quickly detect its unavailability through gossip and route requests to its healthy replicas. When the node comes back online, it uses gossip to quickly get up to speed on the cluster's current state. This peer-to-peer design eliminates the single point of failure that can plague centralized database architectures, significantly contributing to Cassandra's legendary uptime and resilience. 2.6 The Write Path. How data is written to disk. When your application sends a write request to a Cassandra node, known as the coordinator node for that request, a series of events unfolds to ensure durability and efficiency. Commit log. First, the write is immediately appended to a per-node durable file called the commit log. This log is crucial for data recovery. If a node crashes before the data is fully written to disk, the commit log ensures that the data can be replayed when the node restarts, preventing data loss. Memtable, concurrently with writing to the commit log, the data is also written to an in-memory structure called a memtable. The memtable acts as a write-back cache, temporarily holding new data. Memtable flush to SS table. Once the memtable reaches a certain size threshold or sits for a specified amount of time, Cassandra flushes its contents to disk as a new SS table, sorted string table. SS tables are immutable, sorted files on disk that contain your actual data. Once written, they are never modified. This two-stage write process, commit log for durability, memtable for buffering and efficiency, allows Cassandra to achieve extremely high write throughput. 2.7 The read path, retrieving data. When your application sends a read request, the coordinator node that receives the request determines which replicas hold the requested data. Request to replicas. The coordinator sends the read request to the appropriate number of replicas based on the consistency level specified by your application. For example, if you request quorum reads and your replication factor is 3, the coordinator will send requests to at least 2 replicas. Data reconciliation. Each replica that receives the request will look for the requested data in its memtable for recent writes and its SS tables for older data. Version resolution. The replicas send their data back to the coordinator. The coordinator then compares the data across the responsive replicas, using timestamps associated with each piece of data to determine the most recent version. This last write wins approach is central to Cassandra's eventual consistency model. Response to client. The coordinator returns the most recent version of the data to your application. Any inconsistent replicas are updated in the background via read repair. 2.8 Data management, compaction and tombstones. Because writes in Cassandra primarily append data and create new immutable SS tables. Over time, you can end up with many SS tables containing different versions of the same data or containing data that has been marked for deletion. To manage this and maintain read performance and disk efficiency, Cassandra uses processes called compaction and tombstones. Compaction. This is a background process where Cassandra merges multiple SS tables into new, optimized SS tables. During compaction, duplicate versions of data are resolved, only the most recent version is kept, and data marked for deletion, tombstones, is permanently removed from disk. Compaction is essential for keeping Cassandra healthy and reads fast, but it can be resource-intensive. Tombstones. When you issue a delete command in Cassandra, the data is not immediately erased from disk. Instead, Cassandra writes a special marker called a tombstone. This tombstone indicates that the data has been deleted. Just like any other data, tombstones are written to memtables and then to SS tables. They persist until compaction occurs, and the tombstone is older than a configured garbage collection grace period. An excessive number of uncompacted tombstones can negatively impact read performance, as Cassandra still needs to read them to determine what data not to return. 2.9 Fault tolerance features. Hinted handoff. What happens if a node is temporarily down or unreachable when a write is supposed to go to it? Cassandra has a feature called hinted handoff to address this. If a coordinator node attempts to write to a replica and finds it temporarily unavailable, e.g., due to a network glitch or a brief restart, the coordinator will not simply give up. Instead, it will store a hint, essentially a lightweight record of the intended write, locally on its own disk. When the unavailable replica comes back online, the coordinator will then hand off the stored hints to the recovered node, ensuring that the absent writes are eventually delivered as if they had happened live. This mechanism greatly improves write durability and availability, guaranteeing that data meant for an unreachable node isn't lost. Understanding these architectural components, from the simple node to the complex interplay of reads, writes, replication, and self-healing mechanisms, is key to effectively designing and building applications with Cassandra. With this foundational knowledge, we can now move to the most critical aspect for developers: data modeling. Suggested further reading: Apache Cassandra Documentation Architecture. Dive deeper into the specifics of Cassandra's internal components, including details on consistent hashing algorithms, different compaction strategies, and advanced configuration for network topology strategy. Data Stacks Documentation Understanding Cassandra provides excellent visual aids and simplified explanations of the architecture, which can be helpful for solidifying the concepts presented in this chapter. Cassandra, The Definitive Guide by Eben Hewitt, O'Reilly Media. This book offers a comprehensive deep dive into Cassandra's architecture and operational aspects. Chapter 3, The Data Sculptor's Toolkit, Mastering Cassandra Data Modeling. If Chapters 1 and 2 introduced you to the why and how of Cassandra's distributed nature, Chapter 3 is arguably the most critical for any developer. Building scalable and performant applications with Cassandra hinges almost entirely on data modeling. This chapter will fundamentally shift your perspective from relational database design, empowering you to sculpt your data for Cassandra's unique distributed environment. 3.1 The Golden Rule: Query-First Design. Forget everything you know about traditional relational data modeling, where you normalize data to eliminate redundancy, and then figure out how to query it. In Cassandra, the absolute golden rule is query-first design. This means you must identify all the queries your application will perform before you design your tables. Cassandra tables are optimized for very specific query patterns, primarily those that involve looking up data using its primary key. There are no joins, no foreign keys, and no complex aggregations across multiple tables or even across large portions of a single table. Attempting to force a relational schema onto Cassandra is the most common reason for poor performance and painful development experiences. Think of it this way: instead of defining your data's structure and then asking, how do I get the data out? You first ask, what data do I need to get out and how quickly? And then design a table that makes exactly those queries incredibly efficient. This often leads to denormalization, meaning you'll intentionally duplicate data across multiple tables to optimize for different access patterns. While this sounds counterintuitive to a relational mindset, it is a powerful technique in Cassandra. 3.2 Understanding Keys, Partition and Clustering. The heart of every Cassandra table is its primary key. This key is not just for uniqueness. It dictates how your data is distributed across the cluster and how it is organized, sorted on disk within each partition. A primary key is composed of two fundamental parts. Partition key. This is the most crucial component. Its value determines which node, or set of nodes, in a composite partition key a row of data ultimately resides on. Cassandra uses the hash of the partition key to distribute data evenly around the ring. A well-chosen partition key is vital for even data distribution, preventing hot spots, where one node becomes overloaded, and ensuring efficient query routing. Aim for high cardinality in your partition key, meaning a wide variety of unique values, to spread data effectively. The number of rows within a single partition should also be carefully considered. Too many can lead to hot partitions. Clustering columns. These columns determine the physical order of data within a specific partition. They provide a secondary sorting mechanism and contribute to the uniqueness of a row inside that partition. If you query a partition by its partition key, the results will be returned sorted by the clustering columns. You can specify ascending or descending order. The full primary key is defined as primary key, partition key part 1, partition keypart 2, clustering 1, clustering 2. The parentheses around the partition key parts indicate a composite partition key, where multiple columns together form the value that Cassandra hashes for distribution. Example, imagine a table to store measurements from IoT sensors. Query needed. Get all sensor readings for a specific device on a specific day, ordered by time. A good primary key here might be primary key, device seed reading date, reading time. Device seed and reading date together form the composite partition key. This ensures all readings for a single device on a particular day are grouped together and located on the same set of nodes, a single partition. This creates time buckets for a device's data, preventing an active device from creating a single, massive partition over time. Reading time is the clustering column. Within that partition, e.g., device X, Jan 1, 2024, the sensor readings will be stored and retrieved sorted by their exact time. 3.3. The power of denormalization. Duplicating data for performance. Coming from a relational background, the idea of intentionally duplicating data feels wrong. However, in Cassandra, it is a standard and powerful practice. Because there are no joins, if you need to access the same data in different ways, the most performant approach is often to store that data in multiple tables, each optimized for a specific query pattern. Why denormalize? To avoid running multiple queries and complex application-side logic to combine results from different parts of your distributed database. Every query to Cassandra is essentially a distinct lookup based on its primary key. If a piece of data exists across multiple tables, a single write operation in your application would involve inserting it into all relevant tables. Example, user profile and posts. Query 1. Show a user's profile details and all their own posts. Query 2. Show a list of recent posts across all users, including the poster's username. For query 1, you might have a user SPID table. Create table user SPID, userid UUID primary key, username text, email text, and a post spuser table. Create table post spuser, userid UUID, posted UUID, post content text, post date timestamp, primary key, userid, post date with clustering order by post date DASC. For query 2, to avoid querying user SPID for each post to get the username, you could create a denormalized table. Create table recent posts, feeded text, posted UUID, userid UUID, username text, post content text, post date timestamp, primary key, feeded, post date with clustering order by post date DASC. Here, feeded might be a constant string like global feed to group all recent posts into one partition, or a time bucket like todayfeed, etc. When a user posts, your application would perform two insertions, one into post spuser and another into recent posts, duplicating the username and post content. When the user later changes their username, your application would need to update the user SPID table and also update all relevant post spuser and recent posts entries, or accept that old posts might show an outdated username. This highlights the trade-off: increased write complexity for vastly improved read performance. 3.4 Table design patterns. Practical examples. Let's explore some common design approaches. User profile lookup. The simplest pattern. Query by a unique user ID. Users, userid UUID primary key, name text, email text, create a date timestamp. Query. Select from users where userid. Highly efficient. Time series data. Storing sensor readings, logs, or events that occur over time. The key is to avoid unbounded partitions that keep growing indefinitely. Sensor readings, device seed UUID, reading date text, reading time timestamp, temperature float, primary key, device seed, reading date, reading time. Here, reading date could be YYYYMMDD. This creates a new partition for each device per day, keeping partition sizes manageable. Query. Select from sensor readings where device seed equals, and reading date equals, and reading time equals, and reading time less or equal, efficient range query within a day's partition. Last N, or recent items, showing the latest X items. This is often achieved using clustering order by desk and limit. User activities, userid UUID, activated TIMUID, activita type text, activita timestamp, primary key, userid, Active at a timestamp, with clustering order by active at a timestamp DESC. Query. Select from user activities where user it equals. Limit 10. Efficiently gets the 10 most recent activities for a user. 3.5 Working with collections, sets, lists, and maps. Cassandra supports collection data types within columns, which can be very useful for modeling certain kinds of data without having to create separate tables. Set, an unordered collection of unique elements, useful for things like a user's tags on a photo or a list of device capabilities. Create table products, producted UUID primary key, name text, tags settxt. Example value in tags column, electronics, gadget, new. List, an ordered collection of non-unique elements. Useful for maintaining a chronological history, like recent login attempts or a series of comments that can be duplicated. Create table users, userid UUID primary key, username text, login history listTMSTMP. Example value in login history column. 2024 to 1 to 10 10 0 0, 2024 to 1 to 11 11 30 0. Map, a collection of key value pairs, useful for storing flexible metadata or dynamic properties. Create table user settings, userid UUID primary key, prefs maptxt text, example value in prefs column. Theme, dark notifications, enabled language, N. While convenient, large collections, hundreds or thousands of elements, can impact performance, especially for lists where modifications are less efficient. Always consider the expected size of your collections. 3.6 User-defined types, UDTS, structuring complex data. UDTS allow you to define custom composite data types that can be used as column types within your tables. This can improve code readability and allow you to model more complex, nested data structures within a single cell without requiring separate tables or a flat structure. Example: first, define the UDT. Create type address, street text, city text, zip code text, country text, then use it in a table. Create table customers, customrid UUID primary key, name text, shipping address frozen address. The frozen keyword is important. It means the entire UDT value is stored as a single immutable blob, essentially treated as one value. If you want to update just a part of the UDT, e.g., only the city of an address, you'd have to update the entire UDT value. UDTs are beneficial when you have a fixed set of related fields that logically belong together and are always read or written as a unit. They help make your schema more expressive. 3.7 Data model iteration and evolution. It's rare to get a perfect data model on the first try, particularly with a distributed system like Cassandra. Requirements change, access patterns evolve, and unforeseen performance bottlenecks can emerge. Cassandra is designed to be somewhat flexible, adding columns, generally straightforward. You can use alter table ADD column name data type. Existing rows will simply have a null value for the new column until they are updated. This is usually an online operation. Dropping columns, also possible with alter table drop column name. This will mark the dropped column's data with tombstones, which will eventually be removed during compaction. Changing primary keys. This is not possible directly. If your primary key needs to change, e.g., you realize your partition key is causing hot spots, you must create a new asterisk table with the desired primary key and then migrate all your existing data from the old table to the new one. This is a significant operation and requires careful planning and execution, often involving custom application code or batch processing tools. Therefore, while iteration is possible, it's crucial to spend significant time on your initial data model design, especially for your primary keys, as these are the hardest to change. Validate your model with expected query patterns and realistic data volumes before deploying to production. Mastering Cassandra data modeling is an art. It challenges conventional database thinking, but empowers you to build highly scalable, performant, and resilient applications that can handle the modern data deluge. With a solid data model, your application will thrive within Cassandra's distributed ring. Suggested further reading: DataStax Academy, Data Modeling with Apache Cassandra. This free online course from DataStax is highly recommended for hands-on, practical guidance on Cassandra, data modeling principles and patterns. Data Stacks Documentation, CQL Data Modeling. The official documentation provides detailed explanations and examples of key concepts like partition keys, clustering columns, and collection types. Cassandra, the definitive guide, chapter on data modeling, offers a thorough theoretical and practical foundation for designing effective schemas. Chapter 4, Speaking the Language, Apache Cassandra Query Language, CQL, with a foundational understanding of Cassandra's architecture and the crucial concepts of data modeling. It's time to learn how to communicate with the database. Apache Cassandra Query Language, or CQL, is the primary interface for interacting with your Cassandra cluster, allowing you to define your schema, insert data, retrieve it, and manage your database objects. While its syntax might feel familiar to those accustomed to SQL, CQL has fundamental differences rooted in Cassandra's distributed, NoSQL design. 4.1 CQL versus SQL. Recognizing the similarities, understanding the differences. CQL was intentionally designed to resemble SQL to provide a familiar experience for developers. You'll recognize keywords like select, insert, update, delete, create table, and WHERE. This familiarity is a strength, reducing the learning curve for basic operations. However, the resemblance is largely synthetic. Under the hood, CQL operates very differently due to Cassandra's distributed, eventually consistent, and joinless nature. The most crucial differences are no joins. Cassandra does not support SQL-style join operations. All data needed for a query must reside within a single table or be denormalized across multiple tables, handled by your application logic. No aggregation functions across the cluster. You won't find some AVG group by in the traditional SQL sense, or count, that scan the entire dataset. Such operations are typically performed by analytical tools layered on top of Cassandra, like Apache Spark, or by application-level processing of smaller queried result sets. Limited secondary indexing. While CQL supports secondary indexes, they are very different from relational indexes and carry significant limitations. E.g., they often perform poorly on high cardinality columns and can be inefficient for range queries. Your primary key dictates your main query paths. Upset behavior. Insert and update statements are essentially the same operation in Cassandra. They both perform an upsert. Insert if the primary key does not exist, update if it does. In essence, CQL is a language optimized for efficient access to data by its primary key, supporting the query-first data modeling approach. 4.2 Managing keyspaces. The logical database. In Cassandra, all data belongs to a keyspace. A keyspace acts as a top-level container, defining not just a logical grouping of tables, types, and functions, but also the replication strategy and replication factor for all data within it. Before you can create any tables, you need a keyspace. To create a keyspace, you use the create kayspace command. Create kayspace my application data. With replication equals class. Simple strategy, replication factor, 3. Let's break down this command verbally. Create kayspace my application data. This specifies that you want to create a new keyspace named my application data. With replication. This clause defines how data in this keyspace will be replicated. Class. Simple strategy. This indicates the replication strategy. Simple strategy is suitable for single data center deployments. For multi-data center setups, you would typically use network topology strategy, specifying replication factors for each data center. For example, class, network topology strategy, data center 1 name, 3 data center name, 2 replication factor, 3. This means Cassandra will keep 3 copies of every row in this keyspace distributed across your cluster. Once created, you can switch to using a specific keyspace using the use command, similar to how you would select a database in SQL. Use my application data. This sets the default keyspace for all subsequent commands until you use again or end your session. 4.3 Creating tables. The core of your data structure. Tables in Cassandra hold your actual data. As discussed in Chapter 3, create table statements are where you define your columns, their data types, and most importantly, your primary key. The primary key is what dictates data distribution and sorting within a partition. Here's a verbal description of a typical create table statement. To create a new table, you begin with create table followed by your desired table name, for instance, users. Inside parentheses, you list your column definitions, each with a column name and its specific data type. For example, you might define a userid column as a UUID type, username as a text type, and registration date as a timestamp type. After defining all your columns, you must define your primary key. This is done with the primary key clause. You enclose your partition key components within one set of parentheses, and then your clustering columns follow. For instance, primary key, userid, registration date would mean userid is your partition key, and registration date is your clustering column. If you have a composite partition key, you would list multiple columns inside those inner parentheses, like primary key, device ID, reading date, reading time. Example, let's verbally describe creating a table for sensor readings. We'll create a table named sensor readings. It will have a device ID column of UUID type, a reading date column of text type, a reading time column of timestamp type, and a temperature column of float type. The primary key for this table will be device ID and reading date together as the compound partition key, and reading time as the clustering column. This way, all readings for a specific device on a specific date are grouped together, and within that grouping, they are sorted by their reading time. You can also specify clustering order. Create table posts user, userid UUID, posted TIMUID, post content text, post date timestamp, primary key, userid, post date, with clustering order by post date DESC. In this post-spuser table example, post date is the clustering column, and with clustering order by post date DESC ensures that within each user's partition, posts are stored and retrieved in descending order of post date, most recent first. 4.4 Writing data, insert and update. In Cassandra, both insert and update operations effectively perform an upsert. This means that if a row with the specified primary key already exists, an insert will update it, and if it doesn't, an update will insert it. This simplifies application logic. Insert statement. To insert data into a table, you use the insert into command followed by the table name. Then, in parentheses, you list the columns you are providing values for, followed by the values keyword and a corresponding list of values in another set of parentheses. For example, to add a new sensor reading, insert into sensor readings, device ID, reading date, reading time, temperature values. UUID, 2024 to 1 to 20, 2024 to 1 to 2015 30 0 plus 0000, 25.5. You can optionally specify a TTL, time to live, for data to automatically expire after a certain number of seconds. Insert into ephemeralogs, logid, message, values, UUID, important temporary event, using TTL 3600. This log entry will be marked for deletion after 1 hour. Update statement. To update specific columns in an existing row, you use the update command followed by the table name. You then use the set keyword to specify the column value pairs you want to change, and critically, a where clause that identifies the row using its full primary key. For example, to update a user's email. Update user's set email equals new email at example.com, where userid equals UID value. You must provide the full primary key in the where clause for an update. For counter columns, a special numerical type used for things like page views or likes, you use update with plus equals or equals operators. Update page views set viewcount equals viewcount plus 1 where pageit equals UID value, 4.5 reading data. Select statements. Select statements retrieve data from your tables. The key rule here is that to retrieve data efficiently, your where clause must always use the full partition key. You can also filter by clustering columns, but only in the order they are defined in the primary key. To select all columns from a table, you use select from followed by the table name. To specify particular columns, list them instead of the asterisk. Most importantly, you almost always need a where clause to filter the data. The where clause must include all components of your partition key. For example, to get all readings for a specific device on a specific date, Select from sensor readings where device id equals UID value and reading date equals YYYYMMDD. You can then add conditions on clustering columns to get readings for that device and date, but only after a certain time you would add another condition, where device id equals UID value and reading date equals YYYYMMDD and reading time timestamp value. You can also use a range for clustering columns, such as reading time equals start time and reading time less or equal end time. Order by clause. The order by clause works only on the clustering columns as they are defined in your primary key, or in reverse order if specified. You cannot order by arbitrary non-primary key columns without using a secondary index, which has limitations. Limit clause. You can use limit to restrict the number of rows returned by your query. For instance, select from postSPUSER, where userid equals UID value limit 10, will return only the first 10 posts based on the defined clustering order. Allow filtering clause. You may encounter situations where you want a filter on a column that is not part of your primary key or a secondary index. In such cases, Cassandra will force you to add the allow filtering clause to your query. While it allows the query to execute, it's generally an anti-pattern for production environments. Allow filtering forces Cassandra to scan potentially large portions of a partition or even the entire table on one or more nodes to find matches, leading to significantly increased latency and resource consumption. If you find yourself using allow filtering frequently, it's a strong indicator that your data model needs to be reevaluated to better support your query patterns. 4.6 Deleting data. Delete and tombstones. When you delete data in Cassandra, it leverages tombstones, which are special markers that tell Cassandra that a piece of data has been removed. The actual physical removal happens during compaction. You can delete specific columns from a row, an entire row, or even an entire partition using the delete command. To delete a specific column, specify the column name after delete and then from your table, with the full primary key in the where clause. For example, delete email from users where userid equals UID value. To delete an entire row, just use delete from your table with the full primary key. Delete from users where userid equals UID value. To delete an entire partition, you simply provide only the partition key in the where clause. Delete from sensor readings where device id equals UID value and reading date equals YYYYMMDD. This will delete all sensor readings for that device on that specific date. It's crucial to remember that tombstones can impact read performance and storage until they are eventually purged by the background compaction process. 4.7 Batch statements. Atomic operations within a partition. CQL offers batch statements, which allow you to group multiple insert, update, or delete operations into a single logical unit. The key benefit of a CQL batch is atomicity. Either all operations within the batch succeed or none do. You begin a batch with begin batch and conclude it with apply batch. In between, you list your statements. For example, begin batch, insert into users, userid, username values, UUID, Alice, update user settings set theme equals dark, where userid equals UUID, apply batch. Crucial note on batches. While a batch provides atomicity, this atomicity typically applies only to operations that fall within the same partition. Using batches for operations that span different partitions is generally an anti-pattern. While Cassandra will still execute them, it does so by sending individual requests internally, losing the atomicity guarantee across partitions and potentially leading to very poor performance and network overhead, as the coordinator node works much harder. Use batches primarily when you need to update multiple related items within a single logical partition. 4.8 Lightweight transactions, LWTS. Achieving strong consistency. For most Cassandra operations, you design your application around its eventual consistency model. However, there are rare scenarios where you need absolute strong consistency for a single operation, such as ensuring a username is unique before creating a new user or performing a conditional update if EXISTS. For these cases, CQL provides lightweight transactions, LWTS, using if clauses. LWTS use the Paxos consensus protocol to achieve immediate global consistency for a single row operation. You add if EXISDS, if not EXISDS, or if column equals value clauses to your insert or update statements. Example with if not EXISDS for unique creation. Insert into register registers, username, userid values, Jondo, UUID, if not exists. This statement will only insert the new user if a row with that username does not already exist. If it does exist, the operation will fail, and you'll typically get an error indicating that the condition was not met. Performance warning. Lightweight transactions are significantly slower than regular Cassandra writes. They involve multiple network round trips and consensus protocol overhead. You should use them sparingly, and only when absolute strong consistency for a single piece of data is a critical requirement. For most application interactions, embracing eventual consistency is the path to scalability. 4.9 Secondary indexes and materialized views. When to use them. While primary key queries are the fastest, sometimes you need to query data by a non-primary key column. CQL offers two mechanisms, but with important caveats. Secondary indexes. You can create a secondary index on a non-primary key column to allow limited querying on that column. For example, create index on users' email. Allows you to query select from users where email equals test@example.com. Limitations. Secondary indexes are best suited for low cardinality columns, columns with a limited number of distinct values, like user type or status. They are inefficient for like queries or range queries, and can become a performance bottleneck on high cardinality columns, as Cassandra still may need to fan out requests to many nodes to find matching rows. In general, they are not a substitute for proper data model design using primary keys. Materialized views, MVS. A materialized view is essentially a precomputed, automatically maintained, denormalized table based on a base table. It allows you to define an alternative primary key for the same data, without managing the denormalization entirely in your application code. Example, if you had a posts table primarily indexed by posted, you could create a materialized view postsbeauthor with authorid as its partition key, and Cassandra would automatically populate and maintain this view. Limitations. Materialized views add write overhead, as every write to the base table also triggers a write to the view. More importantly, materialized views are eventually consistent with their base table. There's no guarantee the view will be immediately up to date after a write to the base table. They can also be resource-intensive and complex to manage in large-scale scenarios. Use them carefully for specific, well-defined query patterns where the consistency delay is acceptable. Mastering CQL means understanding not just its syntax, but also the underlying architecture that governs its behavior. It's a powerful but opinionated language, designed to facilitate high-performance operations within a distributed database. With this understanding, you are ready to start connecting your applications. Suggested further reading. Apache Cassandra Query Language, CQL Documentation, the official source for all CQL commands, data types, and syntax rules, essential for detailed reference. Data Stacks Documentation, CQL Reference. Data Stacks provides excellent, developer-friendly documentation for CQL, often with practical examples and explanations. Blog posts and tutorials on CQL anti-patterns. Search for articles discussing the dangers of allow filtering, cross-partition batches, and misusing secondary indexes to deepen your understanding of effective CQL usage. Chapter 5. Connecting the dots. Building applications with Cassandra drivers. You've learned why Cassandra is a powerful database, how its distributed architecture works, and how to define your data models and interact with it using CQL. Now it's time to bridge the gap between your application code and the Cassandra cluster. This is where Cassandra client drivers come into play. These language-specific libraries allow your application to seamlessly connect to, send queries to, and receive responses from your Cassandra database. 5.1 Understanding client drivers, your application's gateway. A Cassandra driver is much more than a simple database connector. Unlike traditional relational database drivers that typically rely on standard interfaces like JDBC or ODBC, Cassandra drivers are purpose-built to understand and leverage the unique characteristics of Cassandra's distributed nature. Here's why they are special. Protocol specificity. Cassandra uses its own native binary protocol for communication. Drivers implement this protocol efficiently. Topology awareness. Drivers don't just connect to a single IP address. They are designed to discover the entire cluster topology, including all nodes, their data centers, and their health status. This allows them to intelligently route requests. Load balancing. Drivers distribute queries across multiple nodes to balance the workload and ensure high availability. Failure handling. They are built with retry mechanisms and error handling strategies tailored for distributed systems, gracefully managing node failures or network issues. Asynchronous operations. Most modern Cassandra drivers are designed for asynchronous, non-blocking I/O, which is crucial for building high-performance, scalable applications. Each major programming language, Java, Python, Node.js, C, Go, etc., typically has a dedicated, officially supported driver from data stacks that adheres to these principles. 5.2 Connecting to the cluster. Configuration and best practices. Establishing a connection to your Cassandra cluster is the first step. This usually involves configuring your driver with a few key pieces of information. Contact points. Instead of providing every node's IP address, you typically provide a list of one or more contact points, the IP addresses of a few healthy nodes in your cluster. The driver uses these initial contact points to discover the rest of the cluster's topology through internode communication, gossip, as we discussed in Chapter 2. Once the cluster is discovered, the driver no longer relies solely on these initial contact points. Load balancing policies. This policy dictates how the driver routes requests to the various nodes in your cluster. DC-aware round-robin policy. This is the most common and recommended policy for multi-data center deployments. It prioritizes sending requests to nodes within your local data center, minimizing latency. If all local nodes are busy or unavailable, it can spill over to remote data centers, but this is usually a last resort due to increased latency. Token-aware policy. This policy is often used in conjunction with DC-aware round-robin policy. It tells the driver to attempt to send a query directly to the node that is the designated replica for the partition key being queried. This reduces network hops and improves performance. Retry policies. Distributed systems are inherently prone to transient failures, e.g., a node temporarily being overloaded, a network hiccup, or a compaction process causing a momentary slowdown. A retry policy defines how the driver should react to these failures. It instructs the driver whether to retry a query, and if so, whether to try it on the same node or a different one, and how many times. Carefully configured retry policies are essential for building robust applications that can gracefully handle minor cluster instabilities without failing the user request. Connection pooling. Drivers maintain a pool of open connections to the Cassandra nodes. Instead of establishing a new TCP connection for every query, the driver reuses existing connections from the pool, significantly reducing overhead and improving performance. You can often configure the size of these pools. Verbalizing connections setup. When typically setting up your Cassandra driver in an application, you begin by creating a cluster object or similar construct. You would then specify a list of at least one contact point, which is typically the IP address or hostname of a Cassandra node in your cluster. If you have a multi-data center setup, you would also specify your local data center name to ensure the driver prioritizes nodes closest to your application. Finally, you would build and connect to create a session object, which is your main interface for executing queries. Conceptual Java example for explanation, not direct code block. Cluster equals cluster builder. Add contact point 192.168.1.100, a contact point IP. With port 9042, default CQL port. With load balancing policy, DC-aware round-robin policy builder, data center 1, build. Build. Session equals cluster.connect, my application data, Connect to a keyspace. The above conceptual example would be described verbally, focusing on adding contact points, specifying a port, using a load balancing policy for a specific data center, and then connecting to a session within a keyspace. 5.3 Executing queries. Simple versus prepared statements. Once connected, your application can send SQL queries to Cassandra. There are two primary ways to execute queries. Simple statements. These are raw SQL strings passed directly to the driver for execution. Use cases, primarily for schema operations, create table, alter table, create KEYSBAC, etc., that are executed infrequently. They are also useful for ad hoc queries from a development or debugging console. Drawbacks. For repeated data operations, inserts, updates, reads, simple statements are inefficient. Cassandra has to parse, validate, and plan the query execution every single time, leading to higher latency. They are also vulnerable to SQL injection attacks if user input is directly concatenated into the query string. Prepared statements. This is the recommended and most efficient way to execute repetitive data operations. Mechanism. Your application first prepares a SQL statement with placeholders, question marks, for parameters. The driver sends this statement to Cassandra, which parses it, plans the execution, and returns a statement ID. The driver then caches this prepared statement. For subsequent executions, your application only sends the statement ID and the actual parameter values. Benefits. Performance. Significantly reduces parsing and planning overhead on the Cassandra side, leading to lower latency and higher throughput. Security. Eliminates the risk of SQL injection because parameter values are bound separately and are never interpreted as part of the query itself. Resource efficiency. Saves CPU cycles on both the client, less string building, and server, less parsing. Verbalizing prepared statement flow. Imagine you frequently need to insert new users into your users table. Instead of constructing a full insert statement string, insert into users id name values UUID. Alice. Every time, you would first prepare a statement like insert into users id name values. This prepared statement is then sent to Cassandra once, giving you back a unique identifier. From then on, for each new user, your application just sends that identifier along with the specific user ID and name. Cassandra already knows what to do with it, making it extremely fast. 5.4 Asynchronous operations. Embracing non-blocking I/O. Modern Cassandra drivers are built to be highly asynchronous. This means that when your application sends a query to Cassandra, it doesn't typically wait passively for the response. Instead, it sends the request and immediately gains control back, allowing it to perform other tasks while the query is being processed on the database side. The response, or an error, is then delivered later, through mechanisms like callbacks, promises in JavaScript, or completable futures in Java. Benefits. Higher throughput. Your application can send many queries concurrently without blocking its threads. Better resource utilization. Application threads are not idle, waiting for I/O operations to complete. Increased responsiveness. The application remains responsive to user input or other events while database operations are in progress. Verbalizing asynchronous query. In an asynchronous model, instead of an immediate return of results equals session execute, select. Your application would typically call something like future equals session executizing, select. This future object represents a promise that a result will be available at some point. You can then attach a callback function to this future that will automatically execute when the results arrive, allowing your application to continue processing other requests in the meantime. 5.5 Data mapping. Bridging application objects and database rows. Most Cassandra drivers provide data mapping capabilities. This means you can define Java objects, Python classes, or JavaScript objects that correspond to your Cassandra table rows. The driver, or an additional object mapper layer provided by the driver, can then automatically convert your application objects into Cassandra rows for writing, and vice versa for reading. Similarities to ORMs, object relational mappers. This concept is similar to ORMs in the relational world, but simpler. Because Cassandra lacks complex joins and relationships between tables, The mapping is primarily about converting between language-specific data types and Cassandra's column types and facilitating queries. Benefits: reduces boilerplate code, improves type safety, and makes your application more readable and maintainable by working with familiar programming language constructs rather than raw database row representations. 5.6 Handling errors and retries, building robust applications. In a distributed system, errors are not exceptions. They are part of the normal operational landscape. Effective error handling and retry logic are crucial for building robust Cassandra applications. Cassandra drivers often categorize errors and provide specific exceptions for different scenarios. No host available exception. The driver couldn't connect to any of the specified contact points or discovered nodes. This might indicate a network issue or the entire cluster being down. Write timeout exception, read timeout exception. The query was sent, but not enough replicas responded within the configured timeout period. This could indicate an overloaded node, network latency, or a very large partition requiring a long scan. Unavailable exception. Not enough replica nodes are currently available to satisfy the requested consistency level. This often happens if several nodes are down or unreachable, or if you've set a very high consistency level, e.g., all, when the cluster is not fully healthy. While the driver's built-in retry policies handle many common transient issues, your application should still implement its own comprehensive error logging, and, for certain types of errors, application-level retry logic with exponential backoff. It's also important to ensure operations are idempotent if you plan to retry them, meaning performing the operation multiple times has the same effect as performing it once, to avoid creating duplicate data upon retry. 5.7 Practical application flow, a simple CRUD example. Let's verbally walk through how an application would perform a common sequence involving creating and reading a user in Cassandra. First, your application would establish a connection. It would configure its cluster or equivalent object with the IP addresses of a few Cassandra nodes, specify the desired data center for load balancing, and then connect to a session object, perhaps for a keyspace called user management. Next, to insert a new user, your application would prepare an insert statement. This statement would look something like insert into users, userid, username, email values. The driver would send this to Cassandra for preparation once. Then, whenever a new user registers, your application would take the user's details, bind them to the prepared statement, and execute it asynchronously. The application then continues its work without waiting. To retrieve a user's details, your application would prepare a select statement, such as select userid, username, email from users where userid. Again, this is prepared once. When a user requests their profile, the application binds the userid to the prepared statement and executes it. The response, containing the user's ID, username, and email, is then delivered to your application in the background, perhaps as a row object from which you can extract individual fields, or mapped directly into a user object within your application for easy use. Finally, when your application needs to shut down, it should gracefully close the Cassandra session and cluster connection, releasing resources. Connecting your application to Cassandra via well-designed drivers is fundamental. By understanding how to configure connections, leverage prepared statements, and embrace asynchronous patterns, you can build high-performance, robust, and scalable applications that truly harness the power of Apache Cassandra. Suggested further reading: DataStax Drivers Documentation. Consult the official documentation for the specific Cassandra driver in your preferred programming language, e.g., DataStax Java driver, Python driver, Node.js driver. These resources provide detailed API information, examples, and best practices. Apache Cassandra Native Protocol Specification. For those interested in the low-level details of how drivers communicate with Cassandra, this specification provides insight into the binary protocol. Chapter 6, CRUD Batches and Beyond, Common Operational Patterns. Now that you understand Cassandra's architecture, data modeling principles, and how to connect your applications using drivers, it's time to dive into the everyday operations. Creating, reading, updating, and deleting data, often referred to as CRUD. While the basic SQL commands might seem straightforward, Cassandra's distributed nature introduces important nuances and powerful specialized operations that every developer needs to master. 6.1 The core operations. Create, read, update, delete CRUD. Let's recap the fundamental SQL operations from a practical, application-driven perspective. Create, insert/upsert. In Cassandra, insert statements are inherently an upsert. This means if a row with the specified primary key already exists, insert will update it. Otherwise, it will create a new row. This simplifies application logic, as you don't typically need a separate check for existence before an insert. Application consideration. Always ensure you provide all components of the primary key when inserting. If any part of the primary key is missing, the operation will fail. Read, select. Retrieving data is usually the most frequent operation. As emphasized, reads in Cassandra are optimized for looking up data by its full or partial primary key, specifically the partition key, and then filtering ordering by clustering columns. Application consideration. Design your data model to support your read patterns. Using select without a where clause is generally an anti-pattern, as it can scan an entire table, which is highly inefficient in a distributed system. Always query by partition key. Update. An update statement allows you to modify specific columns in an existing row identified by its primary key. Application consideration. Remember that Cassandra's updates are more like upserts, applied at the column level. If you update a value for a column that already exists, it's overwritten. If you update a value for a column that doesn't exist, it's created. When you update a row, columns not included in the set clause retain their existing values. Example, verbal. If you have a user's table with userid, username, and email, and you update only the email for a given userid, the username for that user remains unchanged. Delete. A delete operation removes data. However, as discussed, deletes in Cassandra are asymmetric. They involve writing a tombstone marker that logically deletes the data. The actual data is physically removed only later during the background compaction process. Application consideration. Excessive deletions, especially for frequently updated data, which effectively create new versions and implicit tombstones, can lead to a buildup of tombstones. Too many tombstones can increase read latency because Cassandra must still process them to identify what not to return. Proper data modeling and understanding your data's lifecycle are crucial to minimize tombstone overhead. 6.2 Counters, specialized increments. Cassandra provides a unique data type called counter specifically designed for atomic increments and decrements. Unlike regular numeric types, counter columns can only be modified using addition, plus equals, or subtraction equals operations. Purpose. Counters are ideal for scenarios requiring highly concurrent, non-transactional increments, such as tracking likes on a post, views on a page, or votes in a poll. How they work. Cassandra handles the incrementation internally, ensuring that concurrent updates eventually converge to the correct total count, even across multiple replicas. This makes them extremely fast for write-heavy increment operations. Limitations. You cannot set a counter to a specific value. You can only increment or decrement it. You cannot mix counter columns with regular columns in the same table in Cassandra 2.1 and later versions. Earlier versions sometimes allowed this, but it was problematic. A table designed to hold a counter must only contain counters and a primary key. You cannot use TTL on counter columns. Counters are eventually consistent. While the final count will eventually be correct across all replicas, a read immediately after an increment might not reflect the absolute latest value. Application example, verbal. Imagine a pageLikes table with Apache as the primary key and a like count column of type counter. To add a like, your application would send an update pageLikes set like count equals like count plus 1 where paged equals your paged. Cassandra efficiently processes this increment. 6.3 Lightweight transactions, LWTS. Ensuring uniqueness and conditional rights. While Cassandra generally favors eventual consistency for performance, there are specific, critical scenarios where you might need stronger guarantees akin to ACID transactions, particularly for ensuring uniqueness or performing conditional updates on a single row. This is where lightweight transactions, LWTS, come in. Purpose: LWTS use the Paxos consensus protocol to provide atomicity, isolation, and consistency for a single write operation against a single partition. Common use cases: conditional updates, performing a write only if a specific condition is met, e.g., update user's balance if their current balance is greater than the withdrawal amount. Unique row creation, most commonly used for insert if not exists scenarios, ensuring that a primary key, like a username or email, is truly unique across the cluster before a new row is created. Syntax: LWTS are performed using if not EXISTS for inserts or if condition clauses for updates in your CQL statements. Example for unique username: verbal. To ensure a username is unique during registration, you would execute an insert statement like insert into registers, username, userid values, user, UUID, if not exists. If a row with user already exists, this statement will not proceed, and your application will receive a result indicating that the if not EXISTS condition was not met. Performance overhead: LWTS are significantly slower than regular Cassandra writes. The Paxos protocol requires multiple network round trips for voting and agreement among replicas. Therefore, they should be used judiciously, and only when absolutely necessary for strong consistency guarantees that cannot be achieved through data modeling or application-level eventual consistency patterns. Overusing LWTs can become a severe performance bottleneck. 6.4 Batch statements revisited: atomic writes within a partition. As briefly mentioned in Chapter 4, batch statements allow you to group multiple insert, update, or delete operations together to be executed atomically. Transactional guarantees: the critical point to remember is that atomicity in a Cassandra batch applies primarily to operations within the same partition. All operations targeting the same partition key, and thus residing on the same set of nodes, are guaranteed to be atomic. Either all succeed or none do. Cross-partition batches: the anti-pattern. While CQL syntax allows you to include operations across different partitions in a single batch, this is a dangerous anti-pattern for performance. If a batch spans multiple partitions, Cassandra breaks it down internally into individual operations, sends them to their respective partitions, and then attempts to execute them independently. There is no atomicity guarantee across different partitions when using a batch. More importantly, cross-partition batches are significantly slower because the coordinator node has to manage requests to multiple, potentially distant, nodes, incurring high latency and increased resource usage. When to use batches safely: when you need to perform multiple writes to multiple tables, but all related to a single logical entity identified by the same partition key. When you are inserting or updating multiple rows within the same partition. Application example: verbal. If you have a scenario where updating a user's profile data table and their recent activity table, both partitioned by userid, need to be atomic, and that user's data logically lives on the same partition, then an apply batch operation including both updates is appropriate. However, if you're trying to update one user's profile and another, unrelated user's profile in the same batch, that would be a cross-partition batch and should be avoided. 6.5 Time to live TTL. Automatic data expiration. Cassandra's TTL feature allows you to specify an expiration time for data at the row or column level. After the specified time, the data is marked with a tombstone and is eligible for removal during compaction. Purpose: ideal for ephemeral data such as session tokens, temporary logs, caching, or compliance requirements where data must be automatically deleted after a certain period. How to use: you specify the TTL value in seconds during an insert or update statement. Example: verbal. To insert a user session token that expires in 1 hour, 3600 seconds, you would use insert into user sessions, sessionid, userid, expira time values, UUID, now, using TTL 3600. You can also apply TTL to individual columns during an update. Considerations: TTL generates tombstones when the data expires. Managing expired data is subject to the same compaction considerations as explicit delete operations. 6.6 Data evolution. Adding and dropping columns. While changing primary key S is a major undertaking, Cassandra offers good flexibility for evolving your schema by adding or dropping columns from existing tables. Adding columns, alter table, ADD. You can add a new column to an existing table using alter table table name, add new column name data type. For instance, alter table users ADD phone number text. Existing rows in the table will implicitly have a null value for the newly added column until they are explicitly updated. This operation is generally online and non-disruptive. Dropping columns, alter table, drop. You can remove an existing column using alter table table name drop column name. For instance, alter table users drop phone number. Similar to row deletions, dropping a column doesn't immediately reclaim disk space. It marks the data with tombstones, which will be garbage collected during compaction. Renaming columns. Cassandra does not directly support renaming columns using an alter statement. To effectively rename a column, you would typically add a new column with the desired name, migrate data from the old column to the new one, often requiring application logic or a batch job, and then drop the old column. This is a more complex operation. Mastering these common patterns and understanding their nuances within Cassandra's distributed model is essential for any developer. By leveraging counters, using LWTs judiciously, applying batches correctly, and managing data lifecycle with TTL, you can build robust and performant applications that scale effectively. Suggested further reading. Cassandra Anti-Patterns. Batches and Tombstones. Look for articles and presentations from experts, e.g., data stacks, Netflix engineers, that deep dive into the common pitfalls associated with batches and managing tombstones. Cassandra CQL documentation, batch statements, and lightweight transactions. The official documentation provides comprehensive details on the inner workings and recommended use cases for these features. Data Stacks Academy, Data Modeling and Advanced CQL. Many online courses and tutorials offer practical examples and considerations for using these patterns effectively. Chapter 7. Optimizing the Flow. Performance and Scaling Strategies. You've designed your data model, crafted your SQL queries, and connected your application. Now, how do you ensure your Cassandra application performs optimally under load and scales gracefully as your data and user base grow? This chapter delves into the critical strategies for achieving high performance and discusses key considerations for scaling your Cassandra cluster. 7.1. Understanding key performance bottlenecks. Before you can optimize, you need to understand what can slow Cassandra down. Common bottlenecks often stem from misapplied relational thinking or a lack of understanding of Cassandra's internals. Uneven data distribution, hotspots. This is perhaps the most common and damaging performance issue. A hotspot occurs when a few Cassandra nodes are handling a disproportionately large amount of read or write traffic compared to others. This usually happens due to a poor choice of partition key that doesn't evenly distribute data. If one node is overwhelmed while others are idle, your cluster's overall performance is limited by that single saturated node. Too many tombstones. As discussed, delete operations and TTLS create tombstones. If your data is frequently updated or deleted, and if compactions aren't efficient or frequent enough, a large number of tombstones can accumulate. Reading data then becomes less efficient because Cassandra must process these markers to filter out deleted data, consuming CPU cycles and potentially increasing read latency. Large partitions. While Cassandra allows very large partitions, millions of rows, gigabytes of data, querying them can be slow, as all data within a single partition resides on a few specific nodes. Reads must scan through potentially massive amounts of data. Repairs and other internal operations can also time out if partitions are excessively large. Read-write amplification. This refers to the ratio of actual disk I/O operations performed by Cassandra compared to the logical operations requested by your application. Operations like compaction, repair, and even tombstone processing contribute to amplification. While some amplification is inherent in Cassandra's design, excessive levels indicate inefficiencies that can put undue strain on your disk I/O. Inefficient queries. Allow filtering, range scans. Queries that force Cassandra to scan entire partitions, allow filtering, or perform large, unconstrained range scans, e.g., querying between two clustering keys over a very large partition, will be inefficient and slow. 7.2 Data Modeling for Performance. Recap and deep dive. Good data modeling is the single most effective performance optimization you can make in Cassandra. It directly addresses the root causes of many bottlenecks. The query-first approach is performance first. Re-emphasize this golden rule. If you design your tables precisely for the queries your application will run, Cassandra can retrieve the data with minimal effort, resulting in optimal performance. Any deviation from this, e.g., trying to perform ad hoc queries where the table structure doesn't support them efficiently, will lead to performance degradation. Choosing the right partition key, this is paramount. Goal: ensure even distribution of data and requests across the cluster. Guideline: choose a partition key with high cardinality and ensure that individual partitions remain under a reasonable size, ideally, not more than 100 MB 1 GB of data per partition, and not more than 100,000 rows, though these are guidelines, not hard limits, and depend on your workload. Avoiding hotspots. If your application mainly queries by customer ID, but one customer, customrid equals 123, generates 90% of your data, then customrid alone is a bad partition key. Consider composite partition keys, e.g., customrid event date, or bucketing, e.g., customrid and a time-based bucket to spread that user's data across multiple partitions over time. Minimizing, allow filtering and secondary indexes. As discussed, rely on your primary key to fulfill your main query patterns. Allow filtering indicates an inefficient query plan and should generally be avoided in production. Secondary indexes are best for low cardinality, background lookup scenarios, not for primary query paths or high-throughput queries. If you need to query by a non-primary key column, strongly consider creating a separate denormalized table optimized for that query. Avoiding large partitions with composite partition keys. For time series data, instead of just deviceid as the partition key, use deviceid, recording month, recording time for extremely chatty devices. This splits a single device's data into smaller, date-based partitions that are easier for Cassandra to manage and query. 7.3 Consistency levels and latency. The consistency level, CL, you choose for your reads and writes directly impacts performance, latency, and availability. The balance: there's a fundamental trade-off. Higher consistency levels, like all or quorum, mean higher latency because the coordinator node must wait for more replicas to respond. Lower consistency levels, like 1 or LOCALONE, mean lower latency, but a higher chance of reading stale data if replicas are divergent. Practical choices. Writes. Often quorum or LOCALQORUM is chosen for a good balance of durability and performance. If extreme write throughput is critical and some data loss is acceptable, e.g., logging, one might be considered. Reads. Similarly, quorum or LOCALQORUM provides a good balance. For browse or feed applications where slight staleness is acceptable for faster response times, one can be used. Tuning read-write repairs. When you perform reads at a consistency level below the replication factor, Cassandra's read repair mechanism attempts to fix inconsistencies in the background. While beneficial for eventual consistency, a high frequency of read repairs can add background load. Adjusting read repair chance can influence this. 7.4 Client driver tuning for application performance. Your application's interaction with the Cassandra cluster through the driver is another crucial layer for optimization. Connection pooling. Ensure your driver's connection pool is adequately sized. Too few connections lead to request queuing and higher perceived latency in your application. Too many can needlessly consume resources on both client and server. The default settings are often a good starting point, but monitor and adjust based on your workload. Request timeouts. Configure appropriate request timeouts in your driver. If a query takes longer than the timeout, your application will receive an error. This prevents your application from hanging indefinitely on a slow Cassandra response, allowing for quicker error handling or retries. Set timeouts realistically based on acceptable latency for your queries. Asynchronous execution. Embrace the asynchronous nature of modern Cassandra drivers. Non-blocking I/O allows your application to achieve higher throughput by sending multiple requests concurrently without waiting for each one to complete. This is key to maximizing concurrency and utilizing available resources. Prepared statements. As covered in Chapter 5, always use prepared statements for repetitive operations. They eliminate parsing overhead on the server side and greatly improve query execution speed. 7.5 Cluster sizing and scaling considerations. From a dev perspective, while detailed cluster sizing is typically an operations task, developers significantly influence it through data model design and query patterns. Understanding hardware impact. CPU, important for compaction, read path processing, and complex queries. RAM, used for memtables buffering writes, block caches improving read-hit rates, and JVM heap. Disk I/O, crucial for writes, commit log, SS tables, and reads from disk. Fast SSDs are highly recommended for production deployments. Network, internode communication, gossip, replication, hints, read-write coordination is network intensive. High bandwidth, low latency networks are essential. Horizontal scaling. Cassandra's greatest strength is its ability to scale horizontally simply by adding more nodes. When you add a new node, it takes on a portion of the data, and traffic is redistributed over more resources. This process is largely automatic thanks to the consistent hashing ring architecture. Capacity planning for developers. Estimate your data volume growth, e.g., we expect 1 TB of data per month, with 100 new records per second. Understand your read-write ratio and throughput requirements, e.g., we need to support 10,000 writes second and 20,000 reads second. Good data models mean you need fewer nodes for the same amount of data and traffic. A poorly modeled application might require double the hardware for the same workload. Test your application with realistic data volumes and load before deploying to production to uncover any bottlenecks. 7.6 Schema evolution strategies. As your application evolves, your data model might need to change. While alter table for adding or dropping columns is straightforward, significant schema changes require careful handling. Adding columns, generally safe with minimal impact. New columns will be null for existing rows. Changing primary keys. This is always a major operation. It requires creating a new table with the revised primary key and then migrating all your existing data from the old table to the new one. This migration typically involves custom batch processing applications, e.g., using Spark, or a custom script reading from the old table and writing to the new. This process needs to be carefully orchestrated to avoid downtime and ensure data consistency. Plan for this well in advance if such a change is anticipated. 7.7 Case Study Insight. Scaling a massive time series dataset. Consider a company collecting real-time operational metrics from millions of devices globally. Initially, their data model for devicemetrics used deviceid as the sole partition key and timestamp as a clustering column. The problem, hotspots quickly emerged. A few super chatty devices, e.g., critical monitoring equipment generating data every second, caused their partitions to grow excessively large, leading to slow reads, dropped writes, and performance issues on the nodes responsible for those partitions. The solution: the team refined the data model using a composite partition key, deviceid, recording day, timestamp. Now, instead of one giant partition for deviceid equals superdevice, data for superdevice is split into smaller daily partitions. Superdevice 2024 to 1 to 1, superdevice 2024 to 1 to 2, and so on. This strategy effectively buckets the data, spreading the load from active devices across more partitions and, importantly, across more nodes. Queries for a specific device's data over a day or range of days remained efficient because they could target specific daily partitions. Queries for longer time periods would involve querying multiple daily partitions, which is still faster than querying one gigantic, overloaded partition. This example illustrates that even well-intentioned initial data models can face scaling issues without careful consideration of potential hotspots and partition sizes. Iteration and understanding your data's patterns are key. Optimizing Cassandra for performance is an ongoing process that starts with data modeling and extends to application-level client tuning and understanding operational best practices. By proactively addressing potential bottlenecks, you can build truly scalable and high-performance applications. Suggested further reading: Cassandra Performance Tuning Guides. DataStax and other community resources publish extensive guides on optimizing Cassandra performance, covering topics like JVM tuning, compaction strategies, and hardware selection in more depth. Effective Cassandra data modeling resources. Revisit materials on data modeling, particularly those focusing on avoiding hot spots and managing large partitions. Benchmark and load testing tools. Explore tools like Cassandra Stress for simulating workloads and identifying performance bottlenecks in your data model and cluster configuration. Chapter 8: Navigating the Pitfalls. Common anti-patterns and best practices. Building a successful Cassandra application isn't just about knowing what to do. It's equally about understanding what not to do. Many common mistakes, or anti-patterns, arise from trying to force Cassandra to behave like a traditional relational database, or from overlooking the implications of its distributed nature. This chapter will highlight these pitfalls and offer best practices to help you avoid them, leading to more robust, performant, and scalable applications. 8.1 The Lure of Relational Thinking. A Common Trap. Anti-pattern. Attempting to normalize your data, creating many small tables, and then trying to join them in your application logic by performing multiple lookups. Using SQL-centric features like where clauses on non-indexed columns without a partition key. Why it's bad. Performance hit. Cassandra thrives on single query, direct access to data within a partition. Simulating joins requires multiple round trips to potentially different nodes, significantly increasing latency and network traffic. Complexity. Your application code becomes complex, fragile, and inefficient as it tries to stitch together data that should ideally be retrieved in a single read. No joins, no foreign keys. Cassandra simply doesn't support these concepts at the database level. Best practice. Embrace denormalization and the query-first data modeling approach. Design specific tables, also called wide rows or materialized views at the application level, for specific queries, even if it means duplicating data. The cost of storage is often negligible compared to the performance benefits of direct, single lookup queries. 8.2 Anti-pattern. Extremely skewed partition keys, hotspots. Anti-pattern. Choosing a partition key that results in uneven distribution of data or requests across the cluster, leading to some nodes becoming overloaded hotspots. This can happen with very low cardinality keys, e.g., country code for a global app, or high cardinality keys where a single key receives disproportionately high traffic, e.g., a superuser getting all the activity. Why it's bad. Performance bottleneck. The hot nodes become a bottleneck, limiting the performance of your entire cluster as requests queue up. Resource exhaustion. Hot nodes can experience high CPU, I/O, or memory usage, leading to timeouts and instability. Reduced availability. If a hot node fails, the impact is much greater as more requests are directed to fewer, already stressed, fallback nodes. Best practice. High cardinality for partition keys. Select partition keys that ensure data is evenly distributed across all nodes. Composite partition keys and bucketing. For data that naturally clusters, like time series or user activities, include additional components in your partition key, e.g., userid, YYYYMMDD, to create time buckets or other logical subpartitions. This effectively limits the size of any single partition and spreads the load. Monitor for hotspots. Regularly monitor your cluster's node performance metrics to identify and address hotspots proactively. 8.3 Anti-pattern. Misusing batches and allow filtering. Anti-pattern batches. Using batch statements for operations that span many different partitions. Why it's bad. As discussed, cross-partition batches do not provide atomicity guarantee and can severely degrade performance. They lead to increased network traffic and higher load on the coordinator node. Best practice. Use batch statements only for operations that involve the same partition key, or when a true micro-batching scenario occurs, e.g., small, idempotent operations on related data that logically belong together and won't span thousands of partitions. Anti-pattern allow filtering, relying on allow filtering for common queries in production. Why it's bad? It forces Cassandra to scan entire partitions or even the entire table to find matching data, bypassing its efficient primary key-based indexing. This is highly inefficient, resource-intensive, and causes dramatically increased latency, especially as data grows. Best practice. Allow filtering is a strong signal that your data model does not support your query efficiently. Redesign your data model so that your queries can directly use the partition key and clustering columns, or create a specific denormalized table for that query. Only use allow filtering for ad hoc, exploratory queries in development, or for very small, non-critical datasets. 8.4 Anti-pattern. Over-reliance on secondary indexes and materialized views. Anti-pattern, secondary indexes. Creating secondary indexes on high cardinality columns, many unique values, or expecting them to provide SQL-like query flexibility. Why it's bad? On high cardinality columns, secondary indexes can lead to very wide rows internally, making lookups inefficient. They create additional write overhead and can cause ghost data issues if not properly managed during deletion. They don't support range queries efficiently. Best practice. Use secondary indexes only for low cardinality lookups where a specific value is expected and the query volume is not extremely high. Example: finding all users with status equals active. Anti-pattern, materialized views. Using materialized views as a general-purpose denormalization tool or expecting them to be immediately consistent. Why it's bad. MVS add write overhead to the base table and can have eventual consistency issues. They can also create performance problems if not carefully designed to avoid large partitions in the view itself. Best practice. MVS are useful for very specific, well-defined query patterns where the consistency delay between the base table and the view is acceptable, and you want Cassandra to manage the denormalization. For critical, real-time read paths, application-managed denormalization is often preferred. 8.5 Anti-pattern. Large partitions and undisposed tombstones. Anti-pattern large partitions, allowing individual partitions to grow unboundedly to millions of rows or multiple gigabytes of data. Why it's bad. Leads to slow reads, slow writes, increased memory usage during operations, and difficulties with repairs and other internal cluster management tasks. Best practice. Design your partition keys to keep individual partitions to a manageable size, e.g., aim for hundreds of thousands of rows and under 1 GB per partition. Use composite partition keys, time bucketing, or other strategies to split large collections of data into smaller, more performant chunks. Anti-pattern, tombstone accumulation. Frequent deletions or updates leading to an excessive number of uncompacted tombstones. Why it's bad. Tombstones consume disk space and can significantly degrade read performance, as Cassandra must scan them to filter out deleted data. If GC grace seconds is too high, tombstones persist longer, exacerbating the problem. Best practice. Understand data lifecycle. Design your data model to minimize frequent updates that create many tombstones. If data is naturally short-lived, use TTL. Ensure timely compaction. Good compaction strategy and sufficient I/O resources ensure tombstones are cleared efficiently. GC grace seconds. While important for hinted handoff, keep GC grace seconds to a reasonable minimum. Default is 10 days, often lower in practice, to prevent tombstones from lingering too long, especially for range repairs. 8.6 Overengineering consistency. Misusing lightweight transactions, LWTS. Anti-pattern. Using lightweight transactions, LWTS, for every write or for operations that don't absolutely require strong consistency, e.g., using if not EXISDS for every new record even if uniqueness is not strictly critical. Why it's bad. LWTs introduce significant latency due to the Paxos consensus protocol's multiple network round trips. They consume more CPU and network resources and drastically reduce your write throughput. Best practice: use LWTs only when absolute, immediate strong consistency for a single row operation is a non-negotiable requirement. This usually boils down to unique constraint enforcement, like ensuring a username isn't taken or critical conditional updates where race conditions cannot be tolerated. For most other operations, embrace Cassandra's eventual consistency model to maximize scalability and performance. 8.7 Best Practice: comprehensive testing of your data model. Best practice: thoroughly test your proposed Cassandra data model with realistic data volumes and workloads before deploying to production. Why it's good: identify hotspots early. Simulate large amounts of diverse data to see if your partition keys are distributing data evenly. Validate query performance. Execute common application queries under load to see if they meet your latency and throughput requirements. Assess resource usage. Observe CPU, memory, and I/O usage on individual nodes to ensure they are balanced and not reaching saturation. Simulate failures. Test how your application and cluster respond to node failures, network partitions, and varying consistency levels. Tools like Cassandra Stress can help simulate workloads. Don't assume a data model that works for a small dataset will scale. Test with data volumes representative of your growth projections. By actively avoiding these common anti-patterns and adhering to the best practices outlined, you can design and build highly performant, resilient, and scalable applications that fully leverage the power of Apache Cassandra, rather than battling against its design principles. Suggested further reading: DataStax blog series on Cassandra anti-patterns. DataStax regularly publishes articles detailing common mistakes and how to avoid them directly from their engineers and experts. Community forums and Stack Overflow. Review common questions and solutions related to Cassandra performance, as many directly address these anti-patterns in a practical context. Real-world case studies of Cassandra performance issues. Look for presentations and blog posts from companies that have shared their experiences with scaling Cassandra, detailing the challenges they faced and how they resolved performance bottlenecks. Chapter 9: Keeping Watch. Essential monitoring and troubleshooting for developers. Even with a perfectly designed data model and well-tuned application code, issues can arise in any complex distributed system. Being able to monitor your Cassandra cluster and quickly troubleshoot problems is a crucial skill for developers. While deep operational monitoring and cluster management are often the domain of dedicated DevOps or SRE teams, every developer working with Cassandra should understand the key metrics, basic tools, and common issues to watch out for, as they directly impact application performance. 9.1 Why developers need to monitor Cassandra. Monitoring isn't just for operations. It directly impacts your application's health and user experience. Application performance correlation. Slow Cassandra queries directly translate to slow application responses or timeouts for your users. Monitoring helps you pinpoint if the database is the bottleneck. Early issue detection. Catching high read-write latencies, too many pending compactions, or rapidly growing disk usage early can prevent a minor issue from escalating into a major outage. Validating data model efficiency. Production monitoring provides real-world feedback on how well your data model performs under live traffic. Are you seeing hotspots? Are your queries efficient? Debugging database interactions. When your application behaves unexpectedly, monitoring and understanding Cassandra's state can quickly help you diagnose if the problem lies within your application's interaction with the database. 9.2 Key metrics for developers to watch. Focus on metrics that directly reflect the user-facing performance and overall health from a developer's perspective. Client-side, driver-level metrics. Query latency, P95, P99, the most important metric. How long do your queries typically take? P95 means 95% of queries complete within this time. P99 measures the latency for the slowest 1%. Spikes here often indicate problems. Throughput, queries per second, QPS, how many read-write operations your application is sending per second. Connection pool utilization. Are there enough connections from your application to Cassandra? Is the pool constantly saturated, indicating a need for more connections or fewer blocking operations? Number of errors retries. A high rate of errors, e.g., timeout exception, unavailable exception, or automatic retries from the driver indicates underlying cluster instability or network issues. Database side, high-level metrics. Read-write latency per table. Similar to client-side, but from Cassandra's perspective. High latencies here point to issues on the nodes themselves, e.g., compaction pressure, I/O bottlenecks. Pending compactions. A growing number of pending compactions means Cassandra is struggling to keep up with merging SS tables and cleaning up tombstones. This can lead to increased disk space usage and slower read performance. Disk usage per node. Rapidly increasing disk usage might signal an accumulation of uncompacted data, tombstones, or simply that you're approaching capacity. Node status, up-down. Is every node in the cluster running and communicating via gossip? Are there any unreachable nodes? CPU memory utilization per node. High CPU could be complex queries, high write volume, or intensive compaction. High memory usage could indicate issues with Java Virtual Machine, JVM, garbage collection, or large memtables. 9.3 Basic monitoring tools and how developers use them. While sophisticated monitoring systems, like Prometheus, Grafana, Datadog, or DataStax Ops Center, are typically deployed at an operational level, developers often need to quickly inspect a running cluster. Several command line utilities and driver capabilities are invaluable. Node Tool. This is a command line administration tool for Cassandra. While many of its commands are for administrators, a few are very useful for developers. Node Tool Status provides a quick overview of the cluster's health. You'll see which nodes are up or down, their status, normal, joining, leaving, and their load. A quick glance can tell you if a node is offline or if data is severely unevenly distributed. Node Tool TP Stats displays thread pool statistics for the current node. This tells you how busy different components of Cassandra are. Looking at active, pending, and blocked counts for thread pools like read stage, mutation stage, or compaction executor can quickly highlight bottlenecks, e.g., too many pending writes, slow reads. Node Tool CF Stats, or table stats in newer versions, gives you statistics for individual tables, column families. This is incredibly useful for spotting issues related to your data model. Read count, write count. Shows traffic on the table. Read latency, write latency, specific latency for this table. Number of keys helps estimate partition count. Space used, total disk space the table consumes, total number of tombstone cells. A high number here might indicate issues if not being cleaned up by compaction. Max partition size, AVG partition size, helps detect large partitions or hot spots related to your data model. Driver-specific metrics. Most Cassandra drivers expose their own set of metrics, e.g., connection pool size, request latency, error counts, that can be integrated into your application's existing monitoring framework. 9.4 Troubleshooting common application-level issues. When your application isn't behaving as expected with Cassandra, here are common issues and how to approach them. Connection problems, no host available exception. Diagnosis, your application can't connect to any Cassandra node. Troubleshooting, verify that the Cassandra service is running on the specified contact points. Check firewall rules, ports 9042 for CQL, 700701 for internode communication. Ensure network connectivity from your application server to the Cassandra nodes. Check Cassandra logs for startup failures. Timeout errors, read timeout exception, write timeout exception. Diagnosis. Your query succeeded on some replicas, but not enough responded within the configured timeout period, or the coordinator node itself timed out. Troubleshooting. Check Node Tool TP stats on the target nodes. Are the read stage or mutation stage thread pools overwhelmed, high pending, or blocked counts? Examine Node Tool CF stats for the relevant table. Are there very large partitions? Is the max partition size unusually high? Are there many tombstones? This might indicate a data modeling issue. Network latency. Are there network issues between your application and Cassandra or between Cassandra nodes? Increase driver timeouts, caution. As a temporary measure, or if your query load truly requires it, you can increase client-side timeouts, but address the root cause rather than just hiding the symptom. Unavailable exceptions, unavailable exception, diagnosis. Not enough replicas are available to satisfy the consistency level for your query. For example, trying an all right when one node is down. Troubleshooting, node tool status. Are nodes marked down or UN, unhealthy? Consistency level. Is your application trying to use too high a consistency level for the current state of the cluster? E.g., using quorum when only 1 out of 3 replicas is up causes this. Adjust the consistency level if your application can tolerate lower consistency or ensure sufficient nodes are online. Data consistency, issues, read timeout exception, unavailable exception, diagnosis. Your application reads stale data or data that should be present is missing. Troubleshooting, consistency level. Are you reading at a very low consistency level, 1, while writing at a higher one? Understand the consistency trade-offs. Read repair, ensure read repair is active and functioning. Tombstones could be related to GC grace seconds and tombstones if deletions aren't propagating or being picked up by reads. Time sync, NTP. Ensure all nodes in your cluster have their clocks synchronized. Cassandra uses timestamps for conflict resolution, last write wins. Out-of-sync clocks can lead to data inconsistencies. 9.5 Logging strategies for Cassandra applications. Effective logging is your first line of defense in diagnosing application-level issues related to Cassandra. Structured logging. Use a structured logging format, e.g., JSON, for Cassandra interactions. This makes logs easier to parse, query, and analyze with log aggregation tools. Key information to log for every Cassandra query or operation. Query string for prepared statements, its ID and parameters. Be careful with sensitive data. Chosen consistency level. Execution time, latency. Success or failure status. Any error messages or stack traces. The Cassandra IP that served the request. Driver tracing. Many drivers provide client-side tracing capabilities. This can provide very detailed per-query information about which nodes were contacted, their latency, and the path the query took through the cluster. This is invaluable after your query has already reached Cassandra, helping to diagnose distributed operation issues. Cassandra's built-in tracing. You can often enable tracing directly in CQL, tracing on, before a query. This will include detailed server-side information about the query's execution path across multiple nodes, including thrift and native protocol requests. 9.6 Practical application. Debugging a latency spike. Let's walk through a common troubleshooting scenario. Your application logs start showing increased latency and occasional timeouts when writing data to Cassandra. Initial check. Application logs. You pull up your application's logs. The driver-level metrics confirm a rise in write latency and write timeout exceptions. This tells you the problem is likely on the Cassandra side or the network between your app and Cassandra. Cluster health check, node tool status. You quickly SSH into one of your Cassandra nodes and run node tool status. All nodes are up and normal, so it's not a node failure causing the issue. You notice the load metric on 1 or 2 nodes is significantly higher than the others, indicating a potential hotspot. Identify bottleneck, node tool TP stats. You run node tool TP stats on the potentially hot node. You observe a high number of pending or blocked tasks in the mutation stage for writes or compaction executor thread pools. This suggests writes are backing up, possibly due to high incoming traffic or slow disk I/O, or that compactions are consuming too many resources. Examine table statistics, node tool CF stats/table stats. Based on your application's complaints, you identify the specific table receiving these writes. Running node tool CF stats keyspace name table name reveals a rapidly increasing max partition size or an unusually high total number of tombstone cells. This is a strong indicator of a data modeling issue causing large partitions, a hot spot, or excessive tombstone accumulation. Correlate and conclude. The combination of an imbalanced cluster load, backed up mutation stages, and rapidly growing unhealthy partitions points to a likely data modeling anti-pattern, e.g., a poor partition key causing a hotspot for specific data. Your next step would be to investigate client access patterns to that table and consider modifying the data model to spread the load more evenly, or adjusting compaction strategies if tombstones are the primary issue. This systematic approach, leveraging key metrics and basic tools, allows developers to quickly diagnose common Cassandra problems and effectively contribute to solutions. Keeping watch over your Cassandra interactions is not just good practice. It's essential for maintaining robust and performant distributed applications. Suggested further reading: Apache Cassandra operations and monitoring documentation. The official documentation provides in-depth explanations of node-tool commands, JMX metrics, and logging configuration. DataStax documentation monitoring Cassandra. DataStax offers comprehensive guides on monitoring, including recommendations for various tools and metrics. Practical troubleshooting guides. Look for community tutorials or blog posts on troubleshooting Cassandra performance or common Cassandra errors for more practical diagnostic steps. Chapter 10: Real-World Resilience. Case studies and advanced considerations. You've journeyed from understanding Cassandra's core philosophy and architecture to mastering data modeling, SQL, and application integration. You've also learned how to optimize performance and troubleshoot common issues. In this final chapter, we'll solidify your understanding with real-world scenarios and discuss some advanced considerations that will shape your future interactions with Cassandra and distributed systems. 10.1 Mastering Complexity. A Global User Profiles Case Study. Imagine building a globally accessible social media platform where users expect instant profile lookups from anywhere in the world. High availability and low latency are non-negotiable. Scenario: a platform needs to store millions of user profiles, username, display name, profile picture URL, location, etc., and retrieve them for display. Users can update their profiles at any time. Data modeling. The core profile table would be relatively straightforward. Create table user profiles. UserID UUID primary key, username text, displayname text, profile picture text, primary key, UserID. The UserID as the partition key ensures efficient lookup of a single user's profile. Multi-data center strategy, conceptual for developers. Given the global requirement, a multi-data center Cassandra deployment is essential. We would define our key space using network topology strategy. For example, assume we have 3 data centers: USEASD, EUWSD, and ASIASOUTHASD. Create KEYSBAC user data. With replication equals class. Network topology strategy. USEASD 3. EUWSD 3. ASIASOUTHASD 3. This configuration specifies that for every row in user data key space, there will be 3 replicas in each of the named data centers. Application-level consistency with LOCLQRUM. When a user in EUWSD updates their profile, their application's API server would connect to the nearest Cassandra data center, EUWSD. The write operation would explicitly use LOCLQRUM as the consistency level. This means the write is acknowledged as soon as 2 of the 3 replicas in EUWSD confirm the write. This ensures low latency for the user. Cassandra's internal replication mechanisms then asynchronously replicate this update to the USEASD and ASIASOUTHASD data centers. Similarly, when a user in ASIASOUTHASD views another user's profile, their local API server queries the ASIASOUTHASD Cassandra data center, again using LOCLQRUM for reads. This guarantees they will see a consistent, majority-agreed-upon version of the profile within their local data center with minimal latency. Trade-offs: eventual consistency for global reach. While LOCLQRUM provides local consistency, it implies global eventual consistency. If a user in USEASD updates their profile, it might take a few milliseconds or even seconds under heavy network load for that update to propagate to EUWSD and ASIASOUTHASD. A user in Europe might briefly see a slightly outdated version of the profile until the replication eventually catches up. This is a deliberate trade-off. In a global system, maximizing availability and local responsiveness often means accepting brief global eventual consistency. Handling conflicts, last right wins. In a multi-master, eventually consistent system like Cassandra, it's possible for the same piece of data to be updated concurrently in different data centers before the updates have fully replicated. For example, user A in USEASD changes their display name to Alice, while user B in EUWESD, also Alice, simultaneously updates their display name to Alicia. Cassandra resolves such conflicts using a last right wins strategy based on the timestamp of the write. The update with the most recent timestamp prevails. Developers need to be aware of this and design applications accordingly, e.g., implementing application-level conflict resolution or ensuring update paths are unambiguous. 10.2 High throughput. An IoT sensor data ingestion case study. Consider a large-scale Internet of Things, IoT, platform ingesting millions of sensor readings per second from devices worldwide. The data needs to be stored efficiently for time series analysis and quick retrieval for a specific device's history. Scenario: millions of smart meters sending electricity usage data every minute. Data modeling for time series. The key here is to design a primary key that prevents hotspots and allows for efficient range queries. Create table meter readings, metered UUID, reading bucket text, reading time timestamp, k-used float, primary key, metered, reading bucket, reading time, with clustering order by reading time ASC. Here, metered is the device identifier. Reading bucket is a conceptual bucket value, e.g., YYYYMMDD for daily buckets or YYYYMM for monthly. Reading time is a timestamp and serves as the clustering column. This composite partition key, metered, reading bucket, ensures that data for any single meter is distributed into daily monthly partitions, preventing a single meter from creating an excessively large partition over time. All readings for a specific meter within a specific bucket, e.g., a day, reside together, ordered by reading time. Write strategy. Given the massive write volume, the application would likely use consistency level 1 for writes, insert into meter readings. This maximizes write throughput and minimizes latency, as only one replica acknowledging the write is sufficient. While this is the weakest consistency, the nature of sensor data, continuous streams, minor data loss acceptable for a single point, eventual consistency is fine, often makes this an acceptable trade-off for scalability. Read strategy. To retrieve a specific meter's data for analysis, the application can issue efficient range queries. Select from meter readings where metered equals, and reading bucket equals, and reading time equals, and reading time equals. This query directly targets the relevant partition and leverages the clustering column for efficient range retrieval. For queries spanning multiple buckets, e.g., a week's data, the application would issue multiple queries, one per bucket. 10.3 Cassandra and the ecosystem. Brief integrations. Cassandra rarely stands alone. It typically integrates with other powerful tools in a modern data architecture. Apache Kafka, a distributed streaming platform. Cassandra is often used as a durable, highly available sink for Kafka data streams. Real-time data from applications or IoT devices flows into Kafka, gets processed, and then persisted in Cassandra for fast lookups by applications. Apache Spark, a unified analytics engine for large-scale data processing. The Spark Cassandra connector allows Spark to read data from Cassandra for powerful batch analytics, machine learning, or complex ad hoc queries, and write process data back. This is common for generating reports or deriving insights from raw data stored in Cassandra. Search technologies, e.g., Apache Solr, Elasticsearch. Since Cassandra's primary key is optimized for direct lookups, it's not ideal for full-text search or complex joins aggregations for search engine-style queries. Data from Cassandra is often streamed to search platforms like Apache Solr or Elasticsearch, which then provide advanced indexing and searching capabilities. 10.4 Cloud deployments. Managed services versus self-hosting. Deploying Cassandra in the cloud offers flexibility, but the choice between self-hosting and using a managed service has significant implications for developers. Managed services, e.g., DataStax Astra, Amazon Keyspaces, Azure Cosmos DB for Cassandra API. Pros: significantly reduced operational overhead. The cloud provider handles infrastructure, patching, backups, upgrades, and often provides auto-scaling. Developers can focus purely on application logic. Cons: less control over low-level tuning and configuration. Can be more expensive for very large, highly optimized clusters. Potential vendor lock-in. Self-hosting on EC2, Kubernetes, etc. Pros: full control over every aspect of your Cassandra deployment: hardware, software versions, advanced tuning parameters, network configuration. Potentially lower cost for experienced teams at extreme scale. Cons: requires significant operational expertise to provision, monitor, maintain, upgrade, and troubleshoot. Higher staffing costs for dedicated SRE ops teams. For many developers, especially those without extensive distributed systems operations experience, managed Cassandra services are an attractive option as they allow you to leverage Cassandra's power without the burden of complex infrastructure management. 10.5 The future of Cassandra and distributed databases. The landscape of distributed databases is constantly evolving, but Cassandra's core principles of decentralization, horizontal scalability, and high availability remain highly relevant. Future trends include increased cloud-native integration, deeper integration with Kubernetes, e.g., Kubernetes operators for Cassandra for easier deployment and management in containerized environments. Performance enhancements, continuous improvements in compaction strategies, storage engine optimizations, and native client drivers. Managed service evolution. Cloud providers will continue to simplify and optimize their managed Cassandra offerings, making them even more accessible. Broader ecosystem role. Cassandra will continue to serve as a high-performance, durable data store in complex data pipelines, integrated with streaming, analytics, and machine learning platforms. 10.6 When is Cassandra the right choice, and when it's not? As you conclude your journey, internalize this critical decision-making framework. Cassandra is an excellent choice when massive data volumes. You anticipate petabytes of data flowing through your system. High write throughput. Your application generates a huge number of writes per second, e.g., IoT, logging, real-time analytics. High availability is paramount. You cannot afford downtime, and you need a system that continues to operate even with node or data center failures. Linear scalability is required. You need to grow your database capacity simply by adding more commodity hardware without complex re-architecting. Your queries are primarily direct lookups. You can design your data model around query patterns that involve looking up data efficiently by a primary key. Eventual consistency is acceptable. Your application can tolerate brief periods of global data inconsistency for the sake of availability and performance. Cassandra is not the right choice when strict ACID transactions across multiple tables are critical. You need strong transactional guarantees that span multiple records or tables, e.g., traditional accounting systems. Complex ad hoc queries and joins are frequent. Your application heavily relies on complex SQL-like joins, aggregations, or analytics across your entire dataset. Low data volumes and simple needs. A simpler, more traditional relational database or even a file system might suffice and be more cost-effective. Your team lacks distributed systems expertise. Operating a large-scale Cassandra cluster requires a specific skill set, though managed services can mitigate this. Distributed by design, Apache Cassandra for the modern developer has armed you with the knowledge to make informed decisions about when and how to build applications with this powerful database. The key to success with Cassandra lies in respecting its distributed nature, embracing its unique data modeling paradigms, and understanding its trade-offs. Go forth and build scalable, resilient systems.